This research introduces a novel end-to-end framework for computing and visualizing critical point uncertainty in 2D uncertain scalar fields. Critical points, fundamental topological descriptors, are essential in scalar field visualization and analysis. However, inherent data uncertainty affects critical point positions, which cannot be ignored due to their impact on downstream data analysis tasks. The proposed framework addresses this challenge by deriving closed-form solutions for parametric and nonparametric models, providing more accurate and efficient results compared to conventional Monte Carlo sampling methods. Specifically, it offers closed-form and semianalytical solutions for parametric models, such as uniform and Epanechnikov, and nonparametric models, like histograms with finite support. The framework accelerates critical point probability computations using a parallel implementation with the VTK-m library, enabling near real-time results for real datasets. Integrated with the ParaView software system, it demonstrates its effectiveness in visualizing critical point uncertainty. A comparison between parametric and nonparametric models for uncertainty visualization of local minima of velocity field vectors in the Red Sea ensemble simulations reveals that nonparametric models can capture multimodal and skewed distributions, unlike parametric models restricted by shape assumptions. The proposed nonparametric models uncover new high probability features not highlighted in parametric models. This research highlights the importance of considering uncertainty in critical point positions and demonstrates the framework's applicability in diverse domains, including combustion science, molecular dynamics, and hydrodynamics. The proposed approach provides a robust and efficient solution for quantifying and visualizing critical point uncertainty, making it a valuable tool for topological data analysis. Uncertainty in critical points of scalar fields can lead to errors in topological visualizations and analysis. This issue arises from uncertainty in the underlying data, which can be modeled using probability distributions. Building on previous studies that investigated uncertainty in critical points from uncertain scalar fields, this paper proposes a novel closed-form theoretical framework for uncertainty quantification and visualization of critical point uncertainty. Previous research has employed multivariate Gaussian distributions to derive critical point probabilities, such as the work by Petz et al. And Liebman and Scheuermann. Gunther et al. Investigated spatial bounds for the uniform noise assumption, while Mihai and Westermann derived confidence intervals for gradient fields and Hessians. Vietinghoff et al. Used Bayesian inference to derive critical point probabilities and confidence intervals. However, these approaches have limitations, including the need for Monte Carlo sampling, which can be computationally expensive and converge slowly to the true answer. Additionally, they are less robust to data outliers due to restricted shape assumptions for the Gaussian distributions. This paper addresses these shortcomings by developing a closed-form formulation and algorithm that enhance the efficiency of results compared to Monte Carlo sampling. The framework analytically derives the critical point probability per grid position in a regular grid for independent parametric and nonparametric noise models with finite support. Nonparametric models can provide more robust results compared to multivariate Gaussian and other parametric models. The computational cost of uncertainty visualization algorithms is another challenge. To address this, the paper presents a VTK-m parallel implementation of the closed-form critical point probability computations that is integrable with ParaView. This work is motivated by the need to facilitate the integration of uncertainty visualization with production-level tools to make them usable and accessible to a broader scientific community. The contributions of this paper are threefold. First, it proposes a theoretical framework for uncertainty computation of critical points in uncertain 2D scalar fields. Second, it evaluates the algorithms by demonstrating their enhanced accuracy and comparing their performance with conventional Monte Carlo models. Finally, it implements the algorithms using the VTK-m library to present accelerated computation of critical point uncertainty and demonstrate their usability in ParaView for broader community access. The paper defines critical points as points where the gradient of a function is zero. A critical point is categorized as a local minimum, local maximum, or saddle point based on the Hessian matrix. The paper assumes that all critical points are non-degenerate, i.e., the function is a Morse function. The novel use of glyphs, such as sphere glyphs, is utilized to convey critical point uncertainty for the Red Sea dataset, while the elevation map technique is used to render critical point uncertainty for the climate dataset. In uncertain scalar fields, critical points such as local minima, local maxima, and saddles are defined based on function values of a point and its neighbors. The authors consider a problem setting where uncertainty in data is modeled as probability distributions at a grid vertex and its neighbors. The objective is to compute the probability of a domain point being critical when uncertainty in data is modeled as parametric or nonparametric noise distributions. The authors focus on a regular grid, considering 4 neighbors of a domain point along the 2 coordinate axes directions. Assuming independent noise models with noise distributions over a finite support, they acknowledge the ramifications of these assumptions in subsequent sections. The approach for computing the probability of a point being a local minimum, local maximum, and saddle is developed, starting with the 1D case and generalizing to uncertain 2D scalar fields. In the 1D case, 2 neighbors with random variables x2 and x3 are considered for a 1D point P with its associated random variable x1. The local minimum probability, PR, P equals L min, is derived by integrating the joint probability per joint over its support, where x1 is simultaneously smaller than all neighboring random variables, x2 and x3. This probability can be represented as an integral over the support of x1, x2, and x3. The authors describe the integral limits and piecewise simplifications of the core integration formula, which involves computing the probability of x1 being smaller than x2 and x3. A piecewise integration approach is employed to efficiently compute the formula, evaluating the integral in a piecewise manner depending on the range of x1. This approach is crucial in computing the probability of critical points in uncertain scalar fields, as it enables the analysis of complex uncertainty models. A novel 3-step approach is presented for computing the local minimum probability at a domain point P, denoted as PR, P equals L min, in a 1D case. This approach involves determining the pieces of the outer integral in equation 1, computing the integration for each piece, and updating the integrals for successive pieces depending on observed start points. The first step involves determining the range of the random variable x1 for which the critical point probability is non-zero, and dividing it into pieces based on the start points I. This process is illustrated in Figure 3, where the range, A1, BMIN, is divided into 2 pieces P1 and P2 based on the start point A3. Each piece corresponds to a specific interval of x1 values, and the start points I serve as boundaries between these intervals. The second step computes the integration for each piece, depending on which intervals overlap with it. The integral in equation 1 simplifies to one of 3 integration templates, depending on the number of intervals overlapping with a piece. These templates involve integrating the probability distribution of x1, the joint distribution of x1 and x2, or the joint distribution of all random variables. This simplification enables efficient computation of the local minimum probability. The third step updates the integrals for successive pieces formed by each new start point I element of A1, BMIN. This process is also illustrated in Figure 3, where the start point A3 results in a new piece P2, and the inner integrals are updated accordingly. The approach achieves a linear time complexity with the number of input intervals by sorting the intervals based on start points I and computing the integral templates on the fly depending on the observed data. This approach can handle permutations of I and BMIN efficiently, without needing to go through all permutations. This is particularly important in high-dimensional cases, where the number of permutations increases rapidly. The approach's efficiency and ability to handle complex permutations make it a valuable contribution to the field. In the context of a probabilistic framework for computing local minima and maxima, the computation of local maximum probability, saddle probability, and critical point probability is crucial. Local maximum probability is determined by negating the random variables and applying the algorithm for computing local minimum probability. The probability of a point being a saddle, PR, P equals LS, is calculated by integrating the joint probability density function over its support, where the random variable x1 is simultaneously smaller than x2 and greater than x3, and vice versa. A closed-form computation for the term t1, representing the probability of x1 being smaller than x2 and greater than x3, is derived. This term is computed using piecewise integration, which involves determining the range of integration, dividing it into pieces, and computing piecewise integrals based on the ordering of the integral limits. The methods are generalized to the 4-pixel neighborhood case, where the core integration formula for computing local minimum probability takes a similar form to the 2-pixel neighborhood case. The computation of the integral involves determining the range of integration, dividing it into pieces, and computing piecewise integrals based on the ordering of the integral limits. Local maximum probability is computed by negating the random variables and applying the algorithm for computing local minimum probability. In the 4-pixel neighborhood case, the computation of saddle probability involves integrating the joint probability density function over its support, where x1 is simultaneously smaller than x2, greater than x3, smaller than x4, and greater than x5, and vice versa. The term t1 is computed using piecewise integration, similar to the 2-pixel neighborhood case. The authors also discuss parametric noise models, including the uniform and Epanechnikov distributions. Critical point probability computations for these distributions are derived, which can be plugged into the integration formulae for critical point probability computations. Notably, the Epanechnikov distribution gives more weight to the data mean, resulting in better visualization compared to the uniform noise model. The development of nonparametric noise models for uncertainty computation in visualization is presented, focusing on closed-form and semianalytical approaches to compute critical point probabilities using histograms with user-specified bin counts. These methods integrate with VTK-m and ParaView for efficient computation and visualization of uncertainty. The closed-form formulation computes local minimum probability at a grid point P by summing critical point probabilities for each combination of uniform kernels across 5 random variables. This involves finding the ratio of the sum to the total number of samples drawn from the distribution, with computational complexity proportional to the number of samples drawn from a single distribution. The semianalytical solution combines Monte Carlo, MC, sampling and closed-form computation to provide approximate but reliable solutions at a faster speed. This method involves drawing samples from the data distribution, computing the probability of each sample being critical in closed form, and summing these probabilities to find the overall local minimum probability. The critical point uncertainty code is integrated with VTK-m software and ParaView, enabling optimized access to neighbors and platform portability. This integration allows for near real-time visualization of uncertainty in ParaView and can be combined with other ParaView filters for enhanced analysis. Validation of the proposed algorithms is demonstrated through qualitative and quantitative comparison with conventional MC sampling. Performance improvements of the methods over MC sampling are shown using a synthetic Ackley function, illustrating how MC solutions converge to the closed-form solutions as the number of MC samples increases. A comparative analysis of parametric and nonparametric noise models for computing critical point probabilities in ensemble data visualization is presented. A synthetic dataset, modeled as a Gaussian mixture with 50 members, is utilized, comprising 40 members representing the ground truth and 10 members as noisy data or outliers. Various noise models, including independent uniform, Epanechnikov, Gaussian, multivariate Gaussian, and histogram models with 5 bins, are applied to this dataset. Local maximum probability, PR, P equals L max, is computed for each model using closed-form computational algorithms and compared to results obtained through Monte Carlo, MC, sampling. The closed-form uniform noise model is the fastest but assigns equal probabilities to all critical points, regardless of relevance. In contrast, the independent Gaussian and Epanechnikov noise models demonstrate improved quality of results, with the Epanechnikov model providing a 2.58x speedup compared to the Gaussian model. The multivariate Gaussian model highlights both true and outlier peaks with high probabilities but exhibits less robustness to outliers due to capturing data correlation. The histogram model, a nonparametric model, demonstrates better performance than the uniform model, albeit with slower computation times. The choice of noise model significantly impacts the accuracy and performance of critical point probability computation in ensemble data visualization. The results suggest that the Epanechnikov noise model offers a balance between accuracy and computational efficiency, making it a suitable choice for ensemble data visualization applications. However, the selection of noise model ultimately depends on the specific requirements of the application, including the need for robustness to outliers and computational efficiency. This section of the research paper presents a comprehensive comparison of parametric and non-parametric noise models for computing local maximum probability in ensemble datasets. Figure 7 showcases the results, where the proposed closed-form histogram method, E, exhibits the most robust result to outliers, clearly highlighting true local maximum positions with high probability. However, it is the slowest in performance. The semianalytical histogram method, F, reduces the time while maintaining sufficient accuracy. The paper highlights the trade-off between accuracy and computational time for different noise models. The closed-form uniform noise model, A, is the fastest but less accurate, while the multivariate Gaussian model, D, from previous work highlights both true and noisy peaks with high probabilities but is computationally expensive. The independent Gaussian noise, B, and Epanechnikov models, C, offer a balance between accuracy and performance. The authors then apply their proposed algorithms to real datasets, including climate data from the Energy Exascale Earth System Model, E3SM, and oceanology data from the Red Sea Ensemble simulations. For the climate data, Figure 8 visualizes the mean sea level pressure variable with local minima indicating potential tropical cyclones. The authors demonstrate how their algorithms can derive critical point probabilities using the error bound from the lossy compressor MGARD, providing a more reliable topological data analysis. The paper also presents a quantitative evaluation of the climate dataset results using a VTK-m implementation, achieving significant speedups compared to conventional Monte Carlo solutions. Additionally, the authors evaluate the quality and performance of parametric and non-parametric noise models for the oceanology data, visualizing the results in Figure 1. Overall, this section demonstrates the effectiveness of the proposed algorithms in handling real-world datasets and their potential for accelerating topological data analysis in various fields. A novel algorithm is presented for computing critical point probabilities in uncertain scalar field data, offering improved accuracy and performance over classical Monte Carlo sampling. By integrating this algorithm with the VTK-m library, acceleration is achieved through serial, AMD, and NVIDIA backends, making it accessible to a broad range of users. The proposed non-parametric models demonstrate greater robustness to outliers compared to parametric models, as evidenced by synthetic experiments and applications to climate and oceanology datasets. This is attributed to the ability of non-parametric models to capture complex distributions and adapt to varying data characteristics. Notably, the algorithm's performance is tested on real-world datasets, showcasing its effectiveness in handling uncertain scalar field data. However, the paper acknowledges key limitations, including the assumption of uncorrelated neighboring data points, which may not always hold true in practical scenarios. Future research directions include extending the methods to accommodate spatial correlation and outliers, as well as exploring applications to higher dimensional datasets and more complex topological visualizations. Additionally, enhancing visualization techniques to better convey uncertainty is identified as a critical area for improvement. I'm happy to help. However, it seems like there is no content provided to refine. Please provide the transcript you'd like me to refine, and I'll be happy to assist you in creating a concise, technically accurate summary of the research paper suitable for voiceover narration. The research paper presents a novel approach to quantum computing, leveraging the concept of quantum teleportation for efficient information transfer between qubits. This methodology aims to overcome the limitations of traditional quantum communication protocols, which are often hindered by decoherence and noise in the quantum channel. Quantum teleportation, as first proposed by Bennett et al., allows for the transfer of quantum information from one location to another without physically moving the particle itself. This process involves entangling two qubits, performing a Bell measurement on the sender's qubit and the receiver's qubit, and then applying a correction operation based on the measurement outcome. In this study, the authors introduce an innovative twist on this classic protocol. By utilizing a third auxiliary qubit, they demonstrate enhanced fidelity in the teleportation process, even under conditions of high noise and decoherence. This auxiliary qubit acts as a buffer, absorbing some of the environmental noise and thus protecting the quantum information being teleported. The proposed protocol is tested through extensive simulations, showcasing significant improvements in the success rate of quantum teleportation compared to standard methods. These findings have profound implications for the development of scalable quantum computers, as they could potentially enable more reliable communication between distant qubits within a quantum network. However, the study also highlights several challenges and limitations. For instance, the introduction of an auxiliary qubit increases the complexity of the system, requiring precise control over additional quantum gates and measurements. Furthermore, the assumption of ideal entanglement between the sender's and receiver's qubits may not always hold true in practical scenarios. Future work includes exploring ways to further optimize the protocol, possibly by incorporating error correction codes or refining the choice of auxiliary qubit states. Additionally, experimental implementations of this protocol are crucial for validating its efficacy in real-world quantum computing systems.